Can anybody give me the name of an Apache project that is not Storm, Spark, NiFi, Kafka? Let's say the name of an Apache project that has to do with data storage.
Apache Arrow.
Sorry?
Arrow.
Yeah. Would you like a green Hadoop?
Sure.
All right, I'm just going to... Oh, very nice. Okay, great. Hi, thanks everyone for joining me. My name is Edgar Orendain. I study computer science at UC Berkeley, and I've been with Hortonworks since 2016, working on Scala and Java applications with Apache NiFi, Storm, Spark, Kafka, NiFi, Ambari. I think I repeated one of those. The thing I'm working on now is re-architecting and implementing one of our offerings. It's a Hortonworks sandbox, so a desktop environment for big data applications. This morning I spoke to a few people, and it seemed like I needed to make a few changes to the presentation. It seemed like people wanted to spend more time learning about the different stages of a big data pipeline, rather than going over code for any one specific service. So I made some changes to the slide, and I'll try to go over them. I'll try to go through everything without too many ums and pauses, because still sort of fairly recent changes. I removed a lot of live coding, but everything that I removed is still in the repo. It'll be available to everybody. Everything here is documented. Most of what we'll go over also have tutorials that go alongside them, and I'll make it all available after the talk. So why this talk? Scala is great. Everybody loves Scala. We all love Scala. But when it comes to big data, one of the main entry points of big data for Scala developers is streaming or machine learning. And these entry points, coupled with the fact that there's a lot of value in streaming and machine learning, it's difficult for us to explore other parts of the big data pipeline. And sometimes when we're given the task of building a pipeline or working with something that's not streaming, maybe data ingestion or data routing, we tend to stick to the things we know. So maybe like a streaming solution where really another tool would be a better fit. So we end up building a data pipeline in ways that are maybe not the best. I'll also cover where it is very important to take Scala-centric approaches in stages of the pipeline where typically Scala isn't around. So how we can improve the pipeline with Scala. So just to sort of set the stage and understand why the pipeline will include some of the services that we go over. Gone are the days where most of our processing is done on data on stationary data. With the not so recent emergence of the Internet of Things, there's a lot of value in real-time data and data from the edge, and not so much working with the data that's been it's coming from data lakes. A lot of the commodity devices that we carry with us have sensors. They can communicate and compute. They can also compute very efficiently. So there's a lot of value in that. The convergence of these has created an unprecedented opportunity for distributed data solutions. If we're talking about 4 zettabytes today, then with exponential growth, it's 44 zettabytes by 2020. We're going to follow a single use case throughout this reference application, and we're going to build the pipeline with this one specific use case in mind. So consider a vehicle dispatch company that delivers cargo from one place to another, and the trucks have sensors installed on them that feed back to some environment. We want the cargo to get to its destination safely but quickly, and so and without accidents. So we perform analytical processing in order to get some actionable insights. What the best routes are, what drivers are being safe, things of that nature. We also want to predict accidents before they happen. So we want predictive analytics on top of prescriptive analytics. And there are a lot of endpoints because you have sensors on every truck and maybe different hubs and web services that you correlate with sensor data. There's a lot of data sources. And we have to be able to intelligently route data from these data sources to what we'll see are a number of services in our backend. So yes, I'll give you guys a chance. But yes, everything should be based on data, and if we're going to get some sort of action from it, it better be reliable. So a quick overview of the architecture that we'll be going over and designing here. So because we're short on time, we're phasing out the Play app with Scala.js, also Spark machine learning. Again, it's all in the repo, and to replace code. Live code examples for each one of these streaming or computing frameworks, we're just going to replace them with Streaming Analytics Manager application. So what we have, so just to sort of define the different stages of the pipeline, we have our edge, the Internet of Anything. The edge involves, in this use case, it's embedded systems, sensors, but really it can be anything. Syndicated, third-party content, data lakes, Twitter feeds, what have you. It's all the edge. The next stage is going to be our data flow management stage, or sort of our data routing stage. That's represented by the Apache NiFi logo. We're going to use Kafka as our message broker to reliably get data from one service to another. We have our streaming/processing/computing stage, which is that box over to the right. Finally, we're going to persist data to some store. In this case, we'll use Druid, but really we want to persist data somewhere. And finally, after analytics are performed, right, with Druid OLAP, we're going to try and visualize the data, get some actionable insights using Superset. And Schema Registry, I'll explain in a bit here. So why Apache NiFi? So first, Apache NiFi is a data flow management system. If you were to do a search for how to ingest data, how to route data from, say, some syndicated content provider to your processing framework, you might get a tutorial about how to do sentiment analysis on Facebook feeds or word count on Twitter feeds. And so you'd probably end up using what you're comfortable with, maybe Spark or Storm or Flink, to bring in the data, process, and then store somewhere. But the problem with always sticking to what we as Scala developers tend to know as like streaming frameworks is they are not very great or as great at routing data and defining data flow as things that already exist. So routing is not trivial. Let's see. Actually, let me just because we're fighting the clock, I'll go over a lot of this in the actual demo. So yeah, so let's open up NiFi and build a flow. Let's see if I get this. Let me share my screen here. Perfect. Yeah. Okay. So this is Apache NiFi. This is going to be where we define, build our flow. So this first node here. So each one of these boxes is called a processor. It is it's processor in the sense that most sort of streaming or ingestion frameworks call them. So this is a processor, and underneath the hood, what we have is a data generation simulator written in Scala, and it's just wrapped around. It's wrapped by a very light API to get this working in NiFi. So this is our edge. This is our simulated edge where data is generated. And so using NiFi, we take different processors and perform either transformations or we check on certain conditions, and we move this data to some sink. Yeah.
Having a little trouble understanding the exact scope of NiFi. Is it fair to kind of dig it down to like a visual programming version of Apache Stream?
Okay, great question. So, there can definitely be some confusion. We have streaming frameworks, we have data flow managers, and then we also have ingestion frameworks, and those are separate. So this is NiFi is really powerful when it comes to helping define data flow. So bringing in, ingesting data from some source, moving it around, performing some logic, figuring out where it needs to go, and then dropping it into a sink. Not so much actually performing computation. It is sort of visual programming in that it uses a drag and drop paradigm. But it's not like this is translated to a single application that runs somewhere. It runs as different sets of different nodes. This processor here is our simulated data. It is you can consider it our edge. We bring in this processor to route data. We have two streams. We have a single stream with two types of data being generated from this processor. And so route on attribute will route truck data, sensor data from the truck over to the left, and traffic data over to the right. If we have time, we'll come back to this, but here we connect to a web service online to enrich the truck data. So we get the geolocation of the truck, we communicate with some API, and we enrich the sensor data with geolocation information. These two we'll come back to. And finally, we have NiFi take the data and publish it to two different Kafka topics. So pretty straightforward. I mean, it's pretty simple. It doesn't seem like we're doing much, but what we're let me get this. What we're doing here is we're routing data, right? We're defining our data flow, and without having to use a design and deploy application like Spark or Storm, where we have to write code, compile it, then deploy it somewhere. Rather it's you drag in a processor, you drag an arrow to another box, and NiFi takes care of where things need to go.
Question about that?
Yeah.
Does the flow get executed on a single host, or can it be distributed across a set of hosts?
Yes, excellent question. So it is distributed, and there's been a movement to get high availability-esque into NiFi, but I can't speak much to that. But yes, it is distributed. Yes.
The visual graph that you show us, can that get auto-generated to actual Scala code, something that you can see in the code?
No, right. So this is not sort of a design and deploy application where you hit compile and it generates some application. Yeah. So simple answer is no, but I can expand on that after if you'd like. We can take it offline, but just to sort of move along here. So, oh,
Unstructured data like tweets and stuff. You
yeah.
write that stuff under the hood. That, I don't know what it's called.
Sorry, can you repeat the question?
For unstructured data like a tweet, you mentioned that you're ingesting that.
Right.
How do you handle that there? Do you write the formatting or the structurization?
Yes, great question. So yeah, so I can touch on that now instead of a bit here. So NiFi is great because it's data agnostic. You can throw in whatever data you'd like, and you tell it exactly how to route it using your defined logic. Structured data, unstructured data, especially now where there's a lot of heterogeneity and incomplete data. You can define where the data goes based on whether it looks incomplete to NiFi, if it's structured a certain way, if it meets some schema, which we'll talk about in a minute. Okay, so you can all that can be defined or specified rather. This is what our two streams of data look like. And so this will come into play in a bit here, but the first one represents the data that we pull in from the truck sensor. So, time, driver ID, name, latitude, longitude, and whether the sensor caught us speeding or not. The second one is congestion information from some web service online or some other sensor maybe outside the truck. So two streams of data. As I mentioned, with NiFi, you can use it to route flows and specify, where how data should move from the edge to some number of endpoints. It's great because you can use it for it lends itself to agile development, so you can use it to debug if there's an issue. NiFi, if some data packet goes to an endpoint that you don't like, you can replay the logic and tell NiFi to instead try a different flow, and it does this, and you can do all this without having to recompile. There's a lot of data provenance built into NiFi, so you can see and track where all the data flows from source to sink. So that is great. There's a little bit of overhead. So whenever you need to do some serious processing, you can either route the data to some sink, some Spark job that takes it over, or instead you can create custom processors to run some processing or computation in the middle of a flow. And to do that, you can wrap your application using the NiFi API to create a processor. So this is just a stub. We won't go over this, but this is it's not what I see. Yes, so we use this stub, and it's available again on the repo in order to build those two custom processors that we have running. If you remember the architecture, the overview of our architecture, we had something called a Schema Registry up top that seemed to have arrows coming from other services into it. Just to sort of gauge how much time we need to spend on schema, how many people here regularly use a serialization library? So protobuf, Avro. Okay, like half. All right. So then, real quick, if you're trying to send data from one service to another, you want to serialize the data, right? You can't just send like a JVM object. You serialize the data, either as like a JSON object or like maybe just a string of bytes or something. The reason you do that is for a number of reasons. One is these different services need to know how to communicate with each other without without having to explicitly be told, hey, you're a service that is responsible for reading customer data, and then you're a service for reading, data from some sort of truck. Instead, you have one application that can handle both, or handle different types of data. So any engineer here knows that that scope creaks and data drift, especially in IoT. The IoT world is very natural. Data drift meaning your data over time as maybe the edge evolves, the data looks different coming into your system. And so with your scope creaking and your data changing, you need to have a strong schema. If your schema isn't strong, if it's brittle, then your application is brittle. And if your application is brittle, then things start to fail and you're in trouble. And so we use schema. We serialize our data packets with some serialization framework. And this is fantastic. But if you have, and if you're coming from like a Scala background where maybe you're managing 25 to 100 different microservices that all expect serialized data, or rather just data to flow in and out. Your processor, excuse me, your services evolve at different rates. And so if you make a change to one part of your pipeline or one part of your service, then you might have to change your schema at every other service, so that they can still communicate with each other. So this can get really cumbersome. And when you develop a big data pipeline and there's a lot of different types of data flowing into your system, it may be very wise to use what is called the Schema Registry. So Schema Registry is a centralized repository for storing your schemas and your serializers and deserializers. And so we won't see an example, but what you can, so imagine a schema registry as a web service that different services, different components communicate with after receiving some serialized data. They ask the schema registry what schema belongs to the data that's flowing in, and and then the service processes it as it should. If a service upstream evolves and it outputs data in a slightly different format, the downstream service will still communicate with Schema Registry, and Schema Registry will tell it, hey, this is the same schema that existed before, only now it's changed a bit. And there's not necessarily a change they need to make to the downstream components to account for this. So there's multiple open source implementations of Schema Registry. There's one by Confluent and one by Hortonworks. So we won't go over registering schema, but here is a stub on exactly how you do it. So it's pretty straightforward. Again, more information in the repo.
How does that compare to using, like, say, protobufs, which is kind of built-in? The built-in assumption is your schema will evolve over time.
Right. So sorry. So I should probably be repeating the questions. So your question was, how does a service like Schema Registry compare to protobuf or any other serialization library where it's sort of taken as granted that your schema is going to evolve? So for one, Schema Registries can deal with schemas in different formats. And so Schema Registry by Confluent, for example, it only works for Avro, and at the moment I think the strongest bridge is to Kafka. But the one by Hortonworks, it deals with Avro serialization or any other serialization. You can also define your own serializers or deserializers, and it works with any number of services, as long as those services can communicate to can communicate with the registry, as opposed to having to, and not necessarily having to be to include specific libraries like like having to know about protobuf ahead of time. Yeah. Is that answer your question? We could all, I'm happy to expand on that a little after, but yeah. So so let's see. So to recap, what our architecture looks like at this point is we've ingested data from the edge. We've used a data flow management system like NiFi to route the data intelligently and reliably to some number of endpoints. In this case, we're using Kafka as our message broker, and we're using Schema Registry to automatically match impedances between what the data looks like when it comes in from the edge and what the data is expected to look like once it hits our sink. So Schema sort of helps us match those impedances automatically, or sort of auto-magically. So now we have data, and we have this data routed to where it needs to be, and we should process this data, maybe, right? Maybe use some sort of streaming framework. So now now it's really easy. We just choose the best streaming framework, right? It's obviously Spark, or if you want, data governance and security, which definitely you want in the enterprise, then you want to use Storm, but then you have the problem of, well, it's it's not really all too sexy when it comes to Scala, so maybe you should there's a lot of issues. So it's actually it's not, of course it's not as simple as we make it out to be, or as we'd want it to be. And a lot of times it comes down to whether you should use a stream processing framework or use a stream processing framework. Like sometimes they do exactly the same thing for your use case. Sometimes you absolutely want to use a specific one. And so this is sort of outside the scope of the talk, but Vladimir is giving a talk tomorrow at 1 p.m. So definitely check that out if you want, sort of to gauge different use cases for different frameworks. So we're just going to quickly build out a topology using Streaming Analytics Manager just in place of demoing the code for Spark Streaming and for Storm and Flink. Let's see. Oh, let me share my screen real quick. So Streaming Analytics Manager. So I've got one. I've got a flow built out here. So it follows it's also a drag and drop paradigm, and it has value from the perspective of of someone who's trying to either build something out quickly, being agile, or if you're not a developer, then you can build out a topology, without necessarily writing any code. So just to sort of go over the logic. Not necessarily to go over Streaming Analytics Manager itself, we're ingesting from the two Kafka topics that that NiFi dumped data into. We're going to perform a join on those two the data. We're going to check to see if the driver performed some sort of violation, like maybe they were speeding, or they got out of their own lane. And if they did perform some sort of violation, we're going to find the average speed and route it to a Druid store. We'll cover Druid in a second. In addition, we also want to we want to send the data before the speed is aggregated, or rather is averaged to a different Druid store. And in addition, maybe we want to persist the data for, in this case, predictive analytics, where, sometime after, not in real time, we want to go back and analyze the data, or just to persist, for a number of different reasons. So let's see. So this is what our topology looks like. Do I have Druid up? Yes, I do. So underneath the hood, just while this thing is running, underneath the hood, Streaming Analytics Manager, it's really just a visual, sort of, it follows a drag and drop paradigm to build an application. But underneath the hood, it's built on top of a unifying model to deploy this application on a number of different streaming engines. So in this case, it's going to use Storm, but it also has bridges for Storm and or excuse me, Spark. And let's see, that's going to take a second to load. So okay, so. Streaming Analytics, so our application, as we saw, routed to a number of sinks. So 2 Druid stores in this case, and HDFS, or HBase, or HDFS. And so the next part of the pipeline is data persistence. Whether that be just for archival purposes, or you want to run some more analytics, post real-time, post real-time range. So for that, there's a number of solutions: Hive, Cassandra, HBase, Druid, or just a few of them. And again, it really depends on what what the state of your data is and the purpose of your data. Whether it's just to dump into cold storage for later, if it's for always-on applications where you need to query the data often, or in our case, if we want to perform sub-second queries where we need information quickly as soon as we can, so that we make sure our drivers are safe. And so for that, we're going to use Druid. We saw Druid a second ago. So Druid is a high-performance column-oriented distributed data store. There was a talk on Druid right before this one. Here we go. So. Okay, great. So, finally, the last part of this of the pipeline, after we've persisted our data, is to get some sort of insight from it. Right? We want to visualize the data. We want to see exactly what kind of analytics were performed, and generally, see what's going on, and not just do some computation and have the data sit there. We use some data exploration and BI tool. In this case, we're going to use Superset, but alternatives are Redash, Metabase, Tableau, Looker. And so let's just jump in here real quick. So the job that we ran a minute ago, the one that processed the data from the 2 Kafka sources and dumped into Druid stores, we have saved to these. Being fed to these 2 data sources, these two cubes, and so again, these are Druid data stores. Superset is able to connect to a number of different databases, Druid being one of them. There's deep integration with Druid. So looking at a dashboard that I built earlier today, this is what we're able to visualize in real time using the data that we find in Druid, which again is being routed. It's being sent to in real time by NiFi, which of course is ingesting it from our edge. So we'll see this update in real time. So there are a number of visualizations. Really, really anything any sort of visualization that you're able to do standalone, you could probably plug it into Superset. It's originally from Airbnb, and it's now an Apache incubated project. Let's actually create a slice. So just to see how easy it is to create a new visualization using the data again that is being processed and fed to is made available to Superset in real time. So let's say you take violation events. We want to group by. Let's see. Let's perform metrics on count. Let's group by the name of the driver, then the type of violation, and finally the route that the violation occurred on. And that should be it. Whoops. And let's get a better visualization. Let's do a sunburst. Yes. And so here's a visualization on the analytics that we're gathering from our generated, our simulated truck sensors in real time. So in this case, 22% of all violations are were done by Rafael, and of those, 8% were because of speeding, and of those, 30% were done on a certain route. And again, all this is updated in real time. Thanks. So all this is done in real time. And again, we have sub-second queries using Druid, our data store. So yes, let's see. Thanks for. Wait, did that not? You guys saw that, right? Yeah. I shared the screen, right? Okay. Okay, good. Yeah.
Do you, you're saying real time, do you have any sort of estimation of, like, from the edge to your queries? The queries are really fast, but, like, what is the whole latency across the entire system?
Yes, great question. So the question was, when I said real time, what exactly did I mean? We can perform sub-second queries using Druid store. But how long, does it take for all that data, for the data to actually get routed and processed? And so you can define all that. Of course, in different parts of the pipeline with NiFi, you can throttle data. When it comes to doing OLAP, or online analytical processing, and analytics with Druid, you can specify a window period. So that you perform analytics on some number of data packets over some time, given some restrictions or whatnot. So in this case, I think we have I think I have it set to like 3 to 5 minutes, and it could be faster. Only this is running on my local environment, so I think I'm giving it like 8 or 9 gigs. So all of this we have running on the laptop with like 9 gigs of RAM. So I had to tone everything down. But of course, on a real cluster, right, you could sort of, yeah.
You had a machine learning thing down there. I know I need to get out to go into it.
Sure.
But somebody's doing feature set extraction in that big box there.
Right. So
that wasn't in your SAM piece. I just wanted to know.
Right. So how that fits in with the use case is we're predicting, and you can find this on the repo. We're predicting driver events before they occur. Given given weather or routes, we can predict when a driver is going to violate, have some sort of violation before it happens.
Which piece is creating a feature set for that?
So that's our streaming framework. Yes.
Using Spark?
Yeah, there's a version that uses Spark, Storm, and then we also have one that uses SAM. And so what happens there is the data is it's transformed. It's transformed to look a specific way, so that our so MLlib sort of has an easy time performing a model of it. Do which bit?
To create those feature sets within the machine learning. So you gotta transform basically four fields.
Right.
Machine learning cares about.
Right. So.
What's the best technology?
I think really, again, it comes down to a number of different things. I'd hate to say one way or another, but really you can use any one of them. We have code examples for using Storm and Spark, and they work just as well, honestly. But yeah.
So I'm grabbing the decode right now. It looks like there's like almost 50,000 lines of XML and only 2,000 lines of Scala.
Oh,
so does that mean
sure.
that's not a shot at it? Does that simply mean that it's that that NiFi is basically we're using XML declarative language to declare our flow, and then NiFi translates that into executable flows, and the Scala code is only like the custom business logic. Is that a good assessment?
Totally off.
The second half was absolutely right, and so there's I have to git push what I have now, so it'll look the repo will look a bit different, and also it's in a different branch. It's not on the master branch.
Oh,
So.
Looks like a totally different thing.
Yeah, but it's mostly the same, so that's my fault. I should have pointed that out. But yes, your assessment was right. So a lot of the XML you see, it's just an exported flow for NiFi. So it's just there to make it easy to sort of to automate your cluster setup process. So it's not actually used in this. It's there so that you don't have to build out the template yourself or the flow yourself.
Which branches are on there? Hadoop 7, 2007,
I will have it named Scale by the Bay after this.
Oh, I see. It's not there. Okay.
Sure. And so I think we're out of time, but really, just had a couple of other things like, what things we withheld, sort of what issues we have that I didn't point out. But otherwise, definitely check it out. The link's on the bottom. It forwards you to the GitHub repo. If you're interested in the environment that we used to run all this, again, it's a local environment. Using anywhere from like 8 to 10 gigs of RAM with an entire it's a single node cluster that runs on your machine. It is a Hadoop cluster. If you're interested in that, check that out. And otherwise, that's it. Thanks a lot.